right, yeah. So we'll share how to do biosignal with multiple amplifiers and different type of sensors. It's a more practical session for this hour. As mentioned by Christoph, I'm originally from Hong Kong. Work for the Hong Kong office. Work a bit in Heidelberg too. When I first joined the company, but now I'm in Vancouver here, enjoying the nice weather, nice environment. So if you come by the West Coast, maybe we can meet up and yeah, feel free to find me. The main thing for different amplifiers, of course, brain-computer interface, collecting a signal from the subject, e.g., ECoG. But for today's talk, of course, some people want to integrate different type of biosignals. So not just EEG or ECoG, could be, let's say, EXG or eye tracker, etc. Converting those type of signals, process it through a computer, making it some type of control signal to control device, providing feedback, forming closed loop system. So a lot of people want to do that. And let's see what type of signals can we record. Traditionally or originally, amplifier records only EEG. But of course, EXG is now enabled. A lot of people doing those for additional control signals. Let's say EMG, you can just place, like say, finger triggering motion, then you can already form another type of control signals. So lots of research lab are starting to integrate more signals control. Let's say GSL, SpO2 sensors, respiration, those are more, from my experience, more psychology experiment use those. They want to see the mental status of the subjects. That's why they integrate those. Then for more, you can add acceleration meter, temperature, knee movement, eye tracker, etc. Maybe some popular topics nowadays would be integrating eye tracker and fNIRS. They want to do multi-modal measurement of the subjects. So there are lots of possibility, as you can see here, not just what I list out here, but there can be much more as long as we can make the device communicate together through the software or through hardware trigger, then you can have multiple module, multiple dimension control of the subjects and the signal itself. For some of you, you may wonder how I can apply all those signals. So I list out some fields of application that you can use. One example is neuropsychology. As mentioned before, EXG signals combined with EEG is pretty popular. Commonly used in epilepsy measurement. For example, epileptic patient in hospital or clinic settings, they have EEG cap mounts on when they're sleeping, also EEG signal. So when epilepsy happens, they can know what's happening in the brain. Their eye movement usually flutter a lot. EXG ECG channels changes. So that's how you combine all the signals for psychology measurement. More recently, we have some clients having mounting 124 channels for ECG mapping. So lots of electrodes on the chest, monitoring kind of like high resolution EMG, kind of similar to this, but monitoring the chest for ECG. For high resolution EMG, we're targeting some muscle group. So some groups are targeting muscle group firing. They want to pinpoint the muscle fiber and the strand that responsible for a motion tracking. Then maybe more practical will be sports science, people combining EMG, ECG, respiration, eye tracker for different type of sports measurement. In those cases, usually people use wireless EEG plus nowadays they're wireless eye tracker, so it's much more convenient. Then all those other sensors can be actually attached to the amplifier itself, so making everything portable, which is quite easy for sports science measurement. Um, some other interesting topic could be aviation. I have some slides later on. Also automotive industry, they want to track how people drive, the driver behavior, also the passenger reaction. Um, some new topics may be marketing. People use eye trackers showing different type of products. Sometimes people even bring the subject to a supermarket, let them to browse the store, seeing what actually attracts them, to pinpoint what marketing strategy works for them. So there, you can see there are lots of application combining with different signal type based on the application itself. You can just incorporate different methodology to improve the research itself. So as I mentioned, there is some publication before, like this one is pretty interesting. Two pilots in a flight simulator. It's not real flight, but a simulator with all the actual controls. They want to see how the brain data changes when they're cooperating. So it's called hybrid scanning study involving more than one amplifier at the same time, monitoring more than one subjects doing the same task. From this research, we can see that the brain-to-brain cooperation interaction between the pilots actually increases over time when they're doing the cooperation tasks. The EEG can be categorized based on the degree of cooperation, and you can pinpoint error and the micro activation of the brain. It's pretty interesting, so you can find this publication online easily. If you just find the title here. The next one is kind of similar, not flight, but driving. So you can see there are two people working on a drive simulator, um, wearing a high density cap, as you can see on the photo. So high density cap using the g.HIamp system, over 100 channels per cap. At the same time, they're integrating different sensors, ECG, EOG for eye tracking, also eye tracking devices, SpO2, GSR. So different psychological state changes while the people are driving. But of course, during the stimulator, there are different things happening on the screen. So they want to see how the driver responds, how the psychological state of the passenger changes. There are lists of publication here too. The last one I share is also for driving, but this time we're talking about driver drowsiness. They're using EEG, EOG eye tracker. In a driving simulator, they want to see how you define drowsiness, and they propose using EEG biomarker, the theta and delta power as a biomarker for drowsiness control. All of this application requires, of course, amplifier. So let me briefly go through what type of amplifier we can use. The most commonly used will be a wireless option, the Nautilus Pro Flexible. I have one here with me. So as you can see here. The good thing for this amplifier is that you can easily detach the strand from the amplifier itself. The amplifier is this small unit which attached to the back of the cap. You can easily change the cap size, the strand type based on the application. This is really ideal for clinical use. Imagine there are patients coming in having different head size and a different need of the strand. Maybe positioning of the electrode is different, or maybe type of electrodes is different. So you can easily pick up the cap you need, use it on patient A. When patient B comes in, you just swap the cap for patient B. So it's really convenient. And good thing is, you can also make it a multi-purpose version. I will show you later on. More traditional device would be Nautilus Research, fixed strand device, but provide up to 64 channels of electrodes. So almost full head coverage. Of course, less number than wired device, but it's good enough for most of the research. This is the multi-purpose device I just talked about. It allows you to connect with different type of sensors too, which fits with today's topic. One example you see on this picture is this lady attaching GSL sensors on her fingers for detecting the sweat from her fingers, which in psychological sense is how nervous or excited she is. Then she's also attaching the EMG sensor on her fourth arm. Everything is attached to the amplifier itself. So you can imagine all the signals will be timestamped automatically, really easy to use for multiple sensors. One technical image I'm showing here is how you do multiple sensors. Traditional EEG device have a one-string strand to the electrode itself. But for this multi-purpose version, we have detachable electrodes, as you can see here. You can detach one EEG electrodes and attach it to different sensors. One example here is having a device with all detachable electrodes. We can sacrifice channels 7 and 8 for attaching sensor 1, for example, GSL sensors, channel 8 for pulse sensors. We can share the common ground with the sensors, making everything hardware control. So everything will be timestamped automatically. So to make things even more interesting, you can combine Nautilus, let's say Tobii eye tracker, which is one of the big brand for eye tracking. They have a version called Tobii Pro Glasses 3. Not sure if anyone used it before. It's the image you see here. It's just a glasses with a little box for sending data to the computer. It's really convenient, it's wireless, so it's a really perfect combination between the EEG and eye tracking. I have client using this for neuromarketing, sending people to supermarket, as I mentioned before. They look at different products, and the eye tracker can pinpoint where the gazing of the subject is. If you see where my mouse cursor is pointing, this is how it looks like when we are tracking the eyes. So the red dot means the subject is focusing on that particular area. So imagine if we are placing like say 10 products in front of the subject, you can already know what type of product is more attractive to the subject. At the same time, we are measuring the EEG in real time. So the eye tracking and the EEG data are synchronized at the same time. You see the brain behavior changes when the subject is gazing at something. Some other application for such combination is contextual cognitive monitoring. So you can see the EEG workload, the mental workload of the subject, while knowing what the person is focusing at. This also allows you to enhance real-life BCI application because the eye tracking data can help you to pinpoint the target location, just like this image. You know where they are gazing at and what interests them. And at the same time, the EEG data from the Nautilus device itself can verify the mental status and improve the BCI response. Let's say you're doing robotic control. If the subject is focusing on certain control movement, let's say moving a car forward, you know that the subject is gazing at a forward control movement. So at the same time, you can co-match the signal data with the EEG data, making the BCI control more robust. Maybe another application is for training and safety. Sometimes companies use it for training their workers, making sure they're following the steps, the instruction, and their gazing matches with the control. Another popular combination will be EEG data plus fNIRS data. So we have a really nice combination with the NIRS device. So you see the bigger optos are from the NIRS Sports 2 device. The smaller one are the gel electrodes from g.TEC. Everything can be combined into one single cap. This is the montage if you're wondering how we put the electrodes and the fNIRS optos together. The number labeled are the EEG electrodes. The blue dots, pure blue dots, are the fNIRS optos. So we can actually support up to 64 channels EEG or even more if you're using another EEG device, plus 32 NIRS optos, making, I think, over 100 fNIRS channels if you're cross-checking all the signals together. Some key application for EEG plus fNIRS combination is for also robust BCI control. As you know, EEG is measuring electric signal, but fNIRS measuring the optical signals. So we're actually applying two methodology for one BCI control, making the control signal more robust. Also, some people use it for cognitive workload monitoring. So it's just a different methodology for measuring the brain. Some people use it for neurorehabilitation, cognitive and neuroscience research, emotion and stress detection, etc. Beside wireless device, we have wired device, of course. The USB-M support up to 16 channels. The difference between the USB-M and Nautilus may be the sampling rate is much higher and it has individual grounding. So if you're combining multiple sensors, sometimes it's actually better to use a wired device. And with the g.HIamp, I also have it here today. I'll show you later on. I'll use it for combining with EEG data. The g.HIamp can support up to 256 channel per single device. We have client using 4 devices at the same time for really high density mapping. Really popular nowadays is using EEG with TMS system. So TMS is a coil you place on top of the brain. There's a electric current going through the coil, which induce electric current inside our brain for brain activation. People use it for rehab purpose and different type of brain research for brain activation and EEG monitoring. So what's good with this device is we have a dedicated hat box for TMS system. It filters out or counter the artifact produced by the TMS system. And we have dedicated electrodes, which is 3 mm thick. The thinness of this electrode allows you to place the coil near the head, which means a higher triggering and higher electric stimulation in your brain, which makes the whole research easier or clinical application easier. It also minimizes the artifact because we have a smaller palette for conducting the EEG signals, which make all the preparation and measurement easier than before. The last application may be the pangolin, a high-density grid electrodes. One grid consists of 16 channels. So you can go up to 1,024 channels. We are client using it along with EOG channels and ECG channels for language mapping. A Japanese group do this research mapping the language system. They place a book in front of the subjects, asking the subject to read the lines line by line. At the same time, they're tracking the eye movement using EOG channels around the eyes, monitoring the heart rates too. At the same time, monitoring the language activation. So it's a really interesting research doing high density grid. You may wonder how you do this. Of course, you need to shave your head in order to place the electro grid. But the good thing is the resolution is much higher than traditional EEG channels, which allows source localization and really pinpointing where are you firing the electric signals. The same principle can be applied for high density ECG or EMG applications. So in general sense, we provide different type of hardware. You can combine with different type of sensors, eye tracker, VR glasses, motion tracker, whatever you call it. As long as we can combine the module together, then we are doing multi-module simulation. So to today's practical sessions, we will go through the system together, but first we need to see what type of software is suitable for multi-purpose measurement. If you're not familiar with our software, this is a layout of what you can choose from the software set. We have different type of amplifier, the wired device, IM, USB-M, and the wireless device Nautilus. All the data will be sent to a master software called g.TEC Suite. Under there, we have a server g.HIsys for processing data and sending data to different software sets. As you can see underneath it, there are different software sets you can use. G Recorder is a more basic software, just allowing you to record data. Some additional function with the Pro version is heart rate monitoring, evok potential analysis, CSA and video recording. If you're doing really simple experiment, let's say EEG plus EKG experiment, you can already directly plug in the cable to the original amplifier and measure everything on the recorder. But if we're talking about fNIRS, eye trackers, more complex devices combination with the EEG, usually we do it through g.HIsys, which is under MATLAB Simulink. There are different toolbox there allowing you to combine the system with the EEG system, either through hardware trigger, LSL layer through online, or different forms of, let's say, Arduino or trigger box. So for complex integration, we recommend doing through HISys. But of course, if you are a master in Python, then you can actually integrate everything by using your own code. But it'll be more time consuming and uh, just not as rapid as g.HIsys model. Some additional thing, maybe BS analysis is an offline toolbox for analyzing the data. So sometimes people record data through g.HIsys, then feedback the data back to BS analysis for classification using a classifier for real-time BCI control. But today's demo, I'll be using the g.HIsys, showing you the toolbox that we can use and how easy it is for rapid prototyping. What we're using is a toolbox called Multi-Device Data Acquisition Toolbox. It supports up to 4 amplifiers at the same time. It can be actually any combination. So for example, USB-M plus 1 Nautilus, no problem. Or you can easily mix different amplifiers together. As long as the maximum number is 4, then we can synchronize the data together. So this model you're seeing here is combining 2 amplifier, displaying the data into 2 scope, recording data into 2 file. But of course, if you know MATLAB Simulink, you can easily change the configuration of the model itself. You can record data into one single file, a bigger file, and visualize the data into one window. It's everything up to you as long as you can build a pipeline and use the multi-device toolbox. Okay, so the first recording we are doing is, let's start from basic EEG recording. I have the device here. So I'll mount myself with the cam. This device is a Nautilus Pro Flexible. The strand I have today is a Sahara strand. Let me switch to the software side. Give me a second. Okay, maybe I show you the device a bit. So this is a Nautilus device, Nautilus Pro Flexible. As you can see, there's a strand coming out here. You can easily detach it and attach different type of strand. This strand is a bit special. It has a multi-purpose connector here. If I'm using EEG with EKG just today, I can actually combine everything using one single amplifier. You can just detach the strand here. It's a 1.5 millimeter touch-proof connector. You can attach with different type of cables, as long as it's a passive cable. Then underneath it, the electrode type is called G-Sahara hybrid. It's a pin-like structure. You can use it as a dry electrodes, or if the signals are not stable, let's say you're wearing the cap running around doing different type of motion or a lot of hand movement, then in those cases, we actually recommend adding some gel to make the signal more stable. The hole in the middle, you can easily use a syringe, add some gel in the middle to fill it up. Then it will transform into gel-based electrode type. So the good thing is you can easily switch between dry and gel base, which makes this cap really easy to use. Okay. So for software, let me see. This is the g.tec suite. If you open g.tec suites, there are different tabs here. What I'm using today is the g.HIsys for online processing. If I click open, it will just pop up the MATLAB window. I've already opened it here before. You go to Simulink, and this Simulink model, the window will open. So you can see g.HIsys includes a lot of libraries and models. You can easily adapt to it. If you have attended the previous session, Johannes already introduced the OSCA. Just in case if you miss it, let me just try this model again. I can show you the data difference. The OSCA is an online filtering toolbox for removing the artifact. It will be quite good to use it as an example today. Once I open the model, you can see it's pre-built for online processing. This block is the multi-device toolbox I mentioned before. We feed the data into this OSCA block for online artifact removal. And this data is unclean. This is after the OSCA toolbox for cleaning the data. The first thing I need to do is to mount the cap and to connect the device. This is the receiver end with a USB cable. This is the transmitter amplifier, which automatically pair with the device itself. So first thing, I will plug in this device for the transmitter. Okay. Then on the transmitter and the Nautilus itself, the power button, press and hold on it. Then you see a light blinking when it is stabilized, which means it has already paired with the receiver end. Okay, then we'll mount the cap. Give me a second. Before I mount the cap, they actually two open strand, as you can see here. One is reference, one is ground. I need to attach the mastoid sticker. Okay, this little mastoid sticker with a little metallic dot on top. You just clip it on the clip itself. Make sure it's tight. Same for the reference. The mastoid stickers stick behind the ear, the mastoid bone, for stabilizing the signal. Usually, if there's someone to help you, it's easier. But for dry setup, doing alone is actually pretty fun. Just take a little bit more time and practice, but it's good. So mastoid sticker behind the ear. Press on it, making sure it's sticking on the skin. And one thing to remember is making sure the sticker is fresh. You don't want it to be stored dry and not sticking on the skin. Okay. Since I'm using dry electrode, one important thing is the pin are actually really touching on the skin itself. So I need to twist each pin a bit, making sure the pin are perpendicular to the skin. The signal are really coming from my head.
Okay. So it seems to be set up already. Let's go back to the software. This is the data acquisition toolbox. We're connecting with the device. I double click on it. It will automatically search for a device on the server. So here you go. I have the g.HIamp the Nautilus connected to the computer. What I'm wearing is the Nautilus. It displays the same serial number here. It's not in use, meaning I can configure it on this window. You click on it, select, then another window will pop out for configuring the amplifier itself. Once again, the serial number will appear, making sure you're configuring the device. The device I have 16 channels, so you can see it's displaying 16 channels here. You can highlight all of them. On the upper left corner are some additional settings you can use. Let's say I want to add acceleration data. The amplifier at the back of the cap, the thing here, actually includes a gyroscope. So you can actually measure the head movement, X, Y, Z axis. This device also have a digital input if you need to trigger the Nautilus. You can also see a link quality, the data communication quality, battery level of the Nautilus. For 16 channels, you can run it for, let's say, 8 hours after a full charge. So it's pretty good. Sampling rates 250 or 500. Let's just use 250 today. Network channels, if there are any interference, which usually not the case, but in case it happens, you can switch the network channels for a more stabilized channel. Some additional setting for each channels on the left-hand side. For using dry electrodes, you want the input range to be higher. So I apply to the channels here. We're not using bipolar. We want to apply bandpass filter for EEG signals. In Canada, the power line interference is 60 Hz, so I applied notch filter. I'm not using common average reference, no noise reduction. So that's it. I click OK. Then you can see the serial number will be updated on the model itself. This is the Oscar live plot. I want to make sure the sampling rate is right. Then, okay, let's try to run it. Oh, let me open up the scope. 16. Okay, let me fine tune. Okay, on the left-hand side is the unclean signal. On the right-hand side, after Oscar. Let me see the scale again. So if I click on this, is channel settings. Channel number 1 to 16 are actually EEG signals. Channel 17, 18, and 19. Remember, I take the acceleration scope. So it's actually g.HIsys acceleration data. You can refine it here and rename the channels number here. Okay. Same for this side. Let me rename it for easier comparison. X1 acceleration. Let's do 150. for EEG data viewing range. Okay. So there's some tests you can do for confirming the EEG signal. The first thing will be ask the subject to relax first, close their eyes to see if there are any alpha wave. Okay. So if you notice the data, there should be a small little bump for the alpha wave. Another test will be ECoG signals. So if I roll my eyes, it usually appear at the frontal region, which is closer to eyes. So let me stop talking for a bit, then roll my eyes, and you'll see data. Then next step you can see is EMG signal. If I clench my teeth, then there should be a huge spike of EMG. So you can see the EEG data is really responsive, but since these are dry electrodes, if there are lots of head movement, of course there are artifacts. But if we're using the OSCA block for artifact removal on the right-hand side, as you can see, the data are mostly clean. I would say 90% clean. Even if I'm speaking, talking a lot, biting a lot, eye movement. Let me do the test again, then you can compare the data. So eye blinking, you see huge artifact here. The OSCA filter it out. Clenching of teeth. Huge artifact again, EMG signals, but through OSCA is gone. So even with dry electrodes, after OSCA, the data is pretty easy to see, which makes the experiment really fast. The main point is rapid prototyping, where you want to do the research and project really fast, trying different things. It will help you a lot using the OSCA Live. If you notice the last three channels is always fluctuating under OSCA, because OSCA is not used for acceleration meter. So it's not useful for the last three channels. If you notice on the unclean data sets, the XYZ, if I try to move my hand, you can actually track the hand movement based on the acceleration meter. Okay, so EEG seems to be working pretty good. Going back to slide, the next task is to combine EEG with ECG data. Today I have the g.HIamp system with me, pretty big device. g.HIamp device. The one I have is a 16-channel device. And g.HIamp comes with different type of head box. The one I'm using is a passive head box. This one with 64 channels available. Passive electrodes. I've already cable connect to my chest. 1.5 millimeter touch-proof connectors. If I don't need all 16 channels on my Nautilus cap, I can actually detach some of the detachable electrodes and just plug in the ECG cable to the cap. But today is about multi-device recording. So I'll be using g.HIamp for ECG recording. You notice there are 3 channels here. I'm actually attaching the electrode strand based on 3-lead system for ECG measurement, the most simple way for measuring ECG. The black one is for grounding, which I attach to the lower rib cage. Channel 1 attached to the right side for signal acquisition. Left side is channel 2 for referencing of signal, and this one is ground. After attaching signal, I can just plug it to the g.HIamp itself. But of course, as you can see on this hat box, there are many holes here. So you can imagine I can attach different type of sensors onto one box, measuring different type of biosignal at the same time. Okay, back to the software. Let's see. We actually built it on the same model. Let me see. If I double click on the data acquisition 2 box again. So there are 2 amplifiers, the g.HIamp and the Nautilus. I need to select both of them to do multi-device recording. Select. The same window pops out. What's different this time is on the top, you'll see 2 amplifier settings. The first one, the serial number, is the g.HIamp. So there are 16 channels for this g.HIamp. I'm using only channel number 1, so just enable channel number 1. We are referencing to channel number 2, so to the other side of the chassis. I'll bipolaring all the channels to channel number 2. The ground is already on the head box, so I don't need to change it. I can apply bipolar reduction, so bandpass filter. For ECG, let's do 0.5 to 100 Hz. Same as before, 60 Hz notch filter. Okay, so this done for the ECG part. Back to the EEG part, same as before. Input range is good. No need to bipolar. EEG bandpass filter 0.1 to 30 Hz. Notch filter at 60 Hz. Okay, let's do the acceleration data again. Maybe battery level too. Now you see the battery level. Okay. Then the configure file will be sent to the device. Let me see. Okay, the first device, the g.HIamp. g.HIamp, we are not passing through the Oscar Live, so just cancel this line. This is data viewing scope. I can connect to the g.HIamp, maybe change it to g.HIamp ECG data. Okay, copying the scope. This one is Nautilus EEG data. This is EEG data after Oscar. Okay. As simple as this, you have already set up the model for viewing ECG and EEG data using one data acquisition 2 box, 2 amplifier, and 3 scope. Then I can start to run. Okay, this ECG data, pretty stable. I'm still alive. Nautilus data, EEG. There are 19 channels, 16 for EEG, 3 for the acceleration, and actually 20. The last one is for battery. And this one is after Oscar. Let me open it up too. Same as before, we can assign amplitude. And assign a channel name. This one is battery level. X-axis, Y-axis, Z-axis. Acceleration data. This one is battery level, so let's do order 0 to 100, I believe. Okay. Setting the same scale for this one. It's not meaningful for acceleration data and battery level after Oscar, so just disable them on the scope. Okay. The heart rate seems pretty good. A little bit of line noise because my table is it's an adjustable table with power cable on it. So if I touch the table, there is some type of noise. But as you can see, the ECG data, you can see the PQRSU peak. It's pretty good. I'm touching my mouse. You see, there's some electric noise coming from my mouse. Okay, so you can see things are really smooth here, really easy to use. I'm already connecting two amplifiers at the same time. ECG data, EEG data running smoothly. Maybe some additional things before we wrap up is if you go to a library browser, g.HIsys, there are different library toolbars on the g.HIsys. If you want to integrate even more things than EKG or multiple amplifier, let's say Tobii glasses, you can actually pull out the block outside from the library to your existing model. Eye tracker, let's say we want to do more. We want to do some data processing and even sending data to another network. There's a LSL layer streaming. You can put out. So this LSL send. We want to process data more. Let's say the EEG data, we want to do bandpass filter. Let me find the bandpass filter here. Okay, let's attach to the unclean data. SL send, we send the data after passing through the bandpass. OP Pro, you define the SL layer. Then if you run it like this, you can see it's really rapid prototyping, be easy to use. Just find the toolbox you need, pull it out, and you can adapt to it. Maybe one more thing to add is there are lots of devices in the market, not just EEG, eye tracker, etc. If you have third-party devices, you want to integrate with our amplifier. A lot of time, software support LSL sense function. So if you're sending control signal from that particular device to this model, you can actually do it through LSL receiver end. You can define the LSL streaming layer, receiving the signal from that third-party device, combined with our model in real time. Or you can use a trigger cable connecting to one of the amplifier itself. The data can be hardware trigger together or combined together through hardware cable. So there are many different ways to combine multi-device for one experiment. Besides SL, you can also use UDP receiver and sender end. Similar principle, different protocol for receiving data through a network. Okay, so we have did that already. SL layer, yeah, as I mentioned, we have sender and receiver end. You can easily define the channels and for complying with different device. Similar for UDP, you define the IP address, receiver and sender, and then you can connect with external device. To recap, nowadays different projects require different biosensors and even different type of trackers, not just biosensors. You can easily combine them through the g.HIsys model. We have different toolbox for you to combine them easily. I've already showed you the amplifier block. You can combine up to 4 amplifiers at the same time, automatically timestamp the amplifier for real-time synchronization. Beside that, you can use UDP interface as our interface for connecting with different devices. So it's really easy to do multi-module experiment in real time for rapid prototyping. It's really up to you how you use the toolbox, how you use the tools for your project. Yeah, if you have any questions, feel free to ask me and we'll try to answer you.
Thank you very much, Mika, for the nice demo. Somebody's asking, how do you find a mastoid bone to place the reference electrode?
Okay. I guess you mean the reference and ground behind. If you touch behind your ear, there's actually a little bone pointing out. Then you can just stick it on there. The reason behind is even if we're talking, the bone is not moving much, which gives a really stable grounding reference for your EEG signals. In some people, they use the ECoG using the same reference, but of course there's some leveling to be tuned, but it's possible too.
Then the Nautilus has an acceleration sensor. Can you use the acceleration sensor to improve the artifact rejection?
I guess there's some algorithm for that, but as you can see from the Oscar demo, it's actually not needed. Everything is processed through the Oscar toolbox, and you don't need to add additional condition to it.
When the EEG traces are already good, why do you actually need the EMG test by clenching your teeth?
It's just a testing of the artifact. It's not necessary, but one of the field steps I usually do to test the response time and whether signals are really reaching.
Then Manuel is saying, thanks, Mr. Ching, you every year improve a bit.
Thank you for attending every year.
Alpesh wants to know which laptop or processor are you using for the experiments?
Okay, so I guess the main determined factor is whether your computer can run MATLAB Simulink. Usually you need 16 GB of RAM, i5 processor, then you're good to go. For my particular computer, I use i7, 16 GB RAM. Then you can see it's pretty smooth.
Okay, thank you very much, Mika.